I'm not used to having the whole thing on. All right, it's recording. Is that blocking? You're good?
Yeah, okay.
All right, I want to get back to where we left off, but I did remember to bring the electroscope this time. And I was going to bring the Van der Graaf generator. So some of this stuff would have been for the Van der Graaf generator. But there's what I call a wand. Basically, it's a dowel about that long, and at the end of it is a metal ball. And it's really convenient for discharging the Van der Graaf generator, especially at this time of year. If this were May or June, I could just let it sit for 2 minutes and it would discharge into the air. But it maintains the charge for quite a bit, as some of you noticed with the PVC pipe that it maintained the charge for a bit. And so it hurts when it discharges through my fingers. So I saw the wand the other day and now I can't find it. So Van der Graaf generator, I might do a demonstration beginning of class or a lab on Wednesday, if I can find it.
You said it had a big metal ball at the end of it?
Yes.
I think I saw you discharging somebody's PVC pipe during the lab.
Do you know what I did with it after that?
I swear you dropped it on the ground and just left it there. But then I don't know what happened to it
I
after
put
that.
it over by the on the left side of the classroom on that table.
Which table?
It's like the countertop on the left side where
The left as you're facing the board?
yes, like over here on this side.
I'm not seeing it on the top of, on the counter over there.
Oh, then I don't know what happened to it then.
Wasn't it inside the box? Of our stuff, the project stuff? Remember how we put everything in there?
But it's, it was put in one of the,
Yeah,
okay.
I think it's in your office or something.
That's why I missed it. All right, mystery solved. All right, so can everyone see the two little bits of foil inside? I'm pretty sure I did not have this last time. All right, so I'm going to charge this up. What's going to happen when I bring it closer to the ball? I'm not going to touch it, but I'm just going to bring it closer.
Will you feel the opposing force?
Will I feel? I probably am not going to. It's going to be too small for me to notice, or to physically feel. I saw a couple of people making hand gestures.
Should repel the aluminum.
Why?
There should be a negative charge going through, and should be a negative charge going through, and being conducted to the foils, and because there's still parts, the negative particles at the end are unpinned, so they'll start repelling each other.
But why would there be a negative charge going through?
Is that what you're transferring from the wand? Because you're going to use the wand to, which typically has a negative charge from what I've seen.
So you're assuming this is negatively charged?
Once you apply the fur to it.
Okay, so, all right. So you're assuming this is negatively charged?
Yes, I'm making that assumption. Or it at least has the same charge. I would
Okay.
say.
All right, so if this is negatively charged and to bring it close to that, what charge is going to, what negative charge is going to be flowing through there?
Going from the one to the ball.
Probably not.
Or not, okay.
I'm not going to touch it yet.
Copy.
So without touching it, I'm not going to. Are you still going to say the leaves are going to split even if I don't touch?
No.
All right, they're just going to kind of hang there.
Right.
All right, anyone have a differing opinion?
Can we assume that this is neutrally charged? Has no charge?
It should be neutrally charged if the two leaves are touching each other. If there were any charge, I could discharge it that way. I'm I have a big enough area so that any excess charge, if those are positively charged, I can give up electrons easily enough. If they're negatively charged, I can take them off. I'm in essence the ground. Alright, so all of you are in agreement with Daniel that if I bring this close but don't touch it, nothing's gonna happen to the leaves.
Well,
No, they're gonna move apart. But
I'm not,
Sorry?
they're gonna move apart.
Why?
That's what I'm saying, I don't know.
Okay.
But I know they're gonna move apart.
You feeling good about that part?
Yeah.
Okay. Brooke, you were saying something?
I was gonna say I don't necessarily agree, I just have absolutely no clue what's gonna happen.
Okay.
yeah, I think they're just gonna, I just can't rationalize why.
Yeah.
I'm gonna move a bit closer so I can like see it better.
Yeah, I feel like I can't.
Of course, you could gamble nothing's gonna happen because it's a physics demonstration. Like that.
You said there's 2 leaves of foil in there?
Yeah.
Oh, I see them now, okay.
Make it slightly silver. Just lift the glass on. I don't know if that's easier to see or not.
Fix the
You don't have
glare.
glare as an excuse, pardon?
Same thought.
Okay.
Oh, it did move apart.
And then when I take it away, they move back together again.
Had you, left the glass on, would they gone back so easily? Or so?
They should have. The glass is just there in case if there were a breeze and the breeze were causing the sway, the glass would prevent that. Alright, so the wand is negatively charged. What do we know about negatively charged things?
Have an excess of electrons.
Okay. And I'm gonna take one thing back. I'm just going to assume it's negatively charged because when I draw this up on the board, it's easier to do minus signs. It could be positively charged.
They have a tendency to want to, do they want to equal out? I think that's the better question. Like, if there's like an access to somewhere, do they want to go somewhere to kind of dissipate or to equalize, if that makes sense?
It depends upon what you're meaning by that. So, when you say equalize, as in the electrons want to distribute evenly throughout the universe?
More or less, but they want to go from like a going from a cluster lead, like where it's all negative to somewhere that is positive. So like a lightning storm, for example.
Okay, so the electrons are drawn, want to go towards some positively charged thing.
Mhm.
They would, but that's neutral, and in theory.
Right.
I know that if the 2 leaves had the same charge, there should be some repelling unless they're stuck together.
Yeah, that's what I was about to ask. So what if, can we say that the charged rod, the charge is being dissipated through the metal, and then when it hits the foil, since they're 2 separate things, does that like charge, since it's the same charge, they like repel?
Alright,
I'm just saying like the charge starts in the rod and it like goes down through.
how does the charge get, it sounded like you're saying that this charge right here goes onto the metal ball and then goes down to the leaves.
Right, because it's a conductor. So,
Alright.
is that
So
possible?
when I take the wand away, does it, the electrons go jumping back?
Oh. That's a good question. Well, there's no negative charge to keep, since it's neutrally charged, there's no like constant charge being given to it.
So the charges that go from here to there sort of get bored and decide to go away?
Like, I guess.
I feel like this is the same conundrum as the straw. Like whatever was happening with the straw seems to be happening here as well.
Yeah.
They're actually, they are 2 slightly different things. I mean, it all still goes back to opposite track like repels. The straw thing has an extra twist to it in the fact that it should have attracted and not repelled at all. So I have a theory about that. I tried to look up, but at some point during that I thought, wait a second, that's wrong, that shouldn't be doing that. And then I went in and internet, and typed in charged object repelling neutral object, and every hit was charged object attracting neutral object, which I could explain. That's the balloon on the wall. But repelling, I have a separate theory. But I'm not 100% sure. But we'll get back to that. All right, so the electrons here, if the electrons first went from there to there, it's dry enough that we're not losing charge into the air at a significant rate. So if any of these charges went down to there, those leaves would still be negatively charged when I pull the wand away, or the rod, whatever it is, and the leaves would still stay apart. So, why do they separate when I bring it close to it? I got my neutral object right here, the leaves. What makes it neutral?
There's no charge.
Ooh, the wording, it may be,
The
you may have
charges are-
intended the right answer, but the way you worded it.
It's not.
The charges are balanced.
Yeah. No charge means there's nothing there, but there's a balance between them. So I have just as many positives and negatives. I'm not gonna draw them all. Those are negative signs. All right. Evenly distributed. You got, I was about to say billions, but even more than that. So you've got, we'll use the scientific term oodles. Oodles of positive and negative charges, roughly equal to the same amount. I bring the negative, this negatively charged, I'm assuming, rod close to it, not touching. Let's go back to rule number 1. Or you have a separate thought.
Yes, I have well, going back to our basic rules, like repels, opposites attract.
Okay.
So I think what's happening is, since there is a large percentage of negatives being introduced, all the negatives from the top to the ball is being pushed down, and there's not enough counteracted to like keep it stable, or to keep it in place. So it's just getting pushed down, causing it to go all the way to the bottom, causing it to repel. And thus, why you bring it back, the
charge.
bottom force brings it back up. I know I'm using wrong words here, but that's kind of the idea.
Yeah, okay, I'll go with the spirit of it. Someone else wants to sort of
You know?
flesh that out any?
No, that makes sense.
The word that came to mind for me was redistribution, like they're not being traded between the two objects, it's just like the charge is being redistributed, the positive charges are coming up.
Ooh,
Let's see, I'm
good.
sorry.
Rule number 2.
Like
the negative
attracts
charges that
like-
move.
Yeah, but then when we pull the object away, they just redistribute back to being even the way that they were.
All right. So this gets close enough. The electrons here hate this. The protons like it. The protons want to get near it, but they're not going to move towards it. Now the leaves do move sort of towards it, but not because the positive charges are attracted. I mean, that's a very, very, very minor effect. This comes towards it, the electrons get scared, and they run away, because electrons hate other electrons. So they come down to here, and they congregate down here, just as was laid out. Now, the two leaves are negatively charged, they will spread apart. Similar to hand on the Van de Graaff generator, where you start getting charged, your hair is charged and starts to spread apart.
Okay, so like, in general, will protons usually never move, but electrons will?
Yeah, pretty much.
Okay.
If you want to move protons, I'm about to move protons. There. That's how you move protons.
But you also just moved electrons.
Yes, I did.
Okay. You can't, yeah, okay, gotcha.
Now, in high energy experiments, you do move protons. You take a hydrogen atom, you expose it to an electric field, which we'll talk about probably next week. The electrons and protons get stripped away from each other, so now you've got a bunch of protons. And so now you have protons, you can shoot protons at top targets. That's in
Wait.
high energy.
But if you take the protons away from, you said you take the protons apart?
So hydrogen atom is just a proton. The most common form of hydrogen is a proton and an electron, with the electron zipping around the proton.
Right.
You expose it to a large electric field, or you got a lot of positive charge here, a lot of negative charge here, you shoot hydrogen into it. Well, the negative charge is going to attract the proton, the positive charge is going to attract the electron, and so they're going to get ripped apart.
And then boom.
And so, well, no, that doesn't cause boom.
Okay.
So now you've got a bunch of protons.
Okay. Gotcha.
If you want boom, you get a couple protons and you slam them into each other.
Okay.
That makes helium, and boom. Essence of the hydrogen bomb.
Alright.
So now so I've got an abundance of negative charges down here. Excess is usually the word that's used, but abundance still works. Abundance of negative charges down here now, and so they spread apart. When I take the wand away, again, the electrons hate each other, so they're gonna go back to going back to being distributed the same way they were before. So they're gonna head back. So whatever I did with it, they're just hidden inside. So I bring it closer, they spread apart, bring it back. So now, if I touch it, what's gonna happen?
The electrons move through, right? Will the electrons move through now that you've touched it?
The electrons from where?
From the wand move through to the rest of the, like the two parts down there.
Okay. The way you were wording it though, it sounds like it's gonna lose all the electrons.
No, it's not gonna lose all of them, it's just some are gonna go down there.
Which ones?
They're the ones towards the edge of the, like, just at the end. Yes.
No, not necessarily. Depends on how you're envisioning. I'm touching it. I picture a God Adam kind of thing.
Yeah.
Okay. Let me generalize it just a little bit. It's the electrons in that local area which
Yeah,
touches the metal ball.
That's what I mean, like the ones that
Let's find out if he's full of himself. Now I take it away. Why do they stay apart?
Because,
Because they equalize kind of, like, this has positive and negative, but more negative, so you touch them together, so now they've kind of shared. So there's an excess in there now as well.
Okay, so they don't leak back. That's what you're going with?
Right.
So this is like charging by contact, correct?
Yes.
Alright, so basically all the, I guess it's, cause remember like what we said earlier, when it was all pushed down, all like the original negative, charges were pushed down, which left a large abundance of positive, charge. So, and all the negative charges from the rod got attracted to the positive and they left there. However, there's still the original, negative charges that basically migrated down, they're still there.
Yeah, okay. And you said one thing, and I might have misunderstood. When I touch it, I heard you say the word all in there. All the electrons, did you
No.
say all the electrons from here?
No, not all the
Okay.
electrons. I probably didn't mean it like, but not all
Okay,
of it.
and it's possible I just jumbled something in my head. All right, so now I have them apart. Again, they would be back together again if this were me. How do I get them to go back to neutral
Grounded.
with,
You can
you
use
could
yourself.
use, yeah. Is it gonna, go back a little bit.
as good as it's gonna get. So, hopefully I grabbed the right rod. Apparently not. Let's try the straw. Alright. Glass. Ooh, what happened there? I didn't touch it. And they're sort of spread apart. Why is it that This one made them go apart, and this one made them come back together.
Are they both the same material?
No.
One's
This is
plastic.
glass.
Okay.
Sorry, I cut you off.
When you're charging these two objects, one has a positive charge and the other is negatively charged?
Yeah. It's as simple as that. So how do you know which one's which?
Well, the glass made it come back together, so I guess that one's positive. But how did you positively charge one and negatively charge another?
Magic.
Did you intend to do that, or did it just?
I was hoping it would do that. I was hoping they'd grab the right materials so that one would, they would do it that way. Trivo. The electric. It touches. I apologize for that. All right, so Trivo electric effect. Go down to here. There we go. I pulled it from 3 different sources. That's why there's 3 different columns there. And I'm not expecting you to be able to see any detail here. Just the green are things that show up in all 4 lists. I think yellow is stuff that shows up in 2 of the lists and something along those lines. But this is sort of a hierarchy of, if you rub 2 things together from this list, the one that's higher up will become positive, the one lower down becomes negative. Now, why does that happen? You start getting into the, I guess, the chemistry of it. So, fur, right there, glass is up there. So glass is higher up, glass is going to be positively charged when I mix it with it. Plastics tend to be down here. There's PVC at the very bottom. Oh, by the way, in the lab, some of you were overcharging because it was so easy to rub when you grab it fur on the PVC. I don't know why this did not occur to me, but it did occur to someone last night. Use one of the other materials. It doesn't charge as well.